Okay, good morning, everyone. So welcome to the lectures on Friday. So remember last time we was talking about norm of vectors. So norm of vectors is just a way to quantify a vector in Rn by a number, okay? And we discussed the one norm, the two norm, and infinity norm, yeah? So the one norm, the infinity, the two norm is just the usual distance on the in Rn, and the one norm, on the plane can be interpreted like a distance of a taxi travel through Manhattan. So Manhattan is in New York, and you see that the street is just like a chessboard, okay? And then we use the norm in order to quantify which matrix is a good matrix and which one is a bad matrix. So we compute, the solution of the linear system from A and from B, and you add a noise. You add a noise, 1% noise, yeah. And then we compare the relative errors, and you can see that the matrix B gives you a very large relative errors. So that is what we stopped last time, okay? So now I want you to move to a new concept, okay? So maybe this is a bit new. So the new concept is the norm of a matrix. Okay, so look at the formula. So the formula say that the norm of the matrix is, you take the matrix A, you multiply with the vector W, and remember the vector W is on the unit circle, so the norm equal 1. And you take the maximal radius, okay? So equivalent to say is you take the ratio of the norm of AV, so any vector V, and you divide it by the norm of vector V. Okay, so it's not easy to visualize this. So maybe let me ask you a question, okay? So suppose I take n equal 2. Let me share the piece of paper, yeah? So suppose I take n equal 2 on the plane, yeah? So n equal 2, what is R2? Okay, and now, okay, so I draw a unit circle. So this is my unit circle, right? Something like this. And then I map the unit circle into an image. Okay, so the map is A multiplied by X. So X comes from here. So X, the vector X comes from inside the circle. So this is my vector X. Okay, so I take all the vector X inside the unit circle and apply the linear transformation AX. Then what do I get? So what do I get on the image? Any guess? Might be something stretch or squish. Yes, but how does it stretch? I mean, what is the shape of the image in general? It's a circle if A is identity. Okay, so maybe let me make a bit more concrete, yeah? So suppose I take A to be, say, 1, 2, yeah? So this one is just diagonal matrix, okay? So if I take the vector E1, so my E1 will be, so now this one is your linear algebra, yeah? So E1 is just 1, 0, okay? So then AE1 will be right here. Okay, so this one is AE1. Yeah. And then E2 will be 0, 2, right? So E2 is 0, 2, right? Sorry, E2 is 0, 1, yeah? Then AE2 is just 0, 2. Okay, so where is 0, 2? So 0, 2 is right here. So AE2 is here. Okay, so now, so E2 is here, yeah? So E2 is here. So now, what is the shape of the image? Is it a circle? So oval, exactly. So we've been oval like this. Okay, yeah. So in general, you know, I mean, I wrote a simple MATLAB program to compute the image. So I can show you the simple MATLAB program. So 1 minute, so I go into the correct directory. So suppose I have just a very general matrix, yeah. So you can see that. Okay, so now let me share my MATLAB screen, yeah. We share the whole screen, yeah, so you can see that. So you see my MATLAB here. So people can see my MATLAB, yeah. So what it is here. So what I'm doing is I plot the circle, yeah. So this one is the radius of the unit circle, right? So radius of the unit circle, yeah. And this one is the center of the unit circle, okay? And so this one is just the parameterization. So this one is the theta, and theta k, okay? Theta k is just 2 pi. Well, I mean, it just you see it's a vector, right? Start from 0, stop at 2 pi, right? And the step is pi over 50. So you can imagine, right? So theta, you just cut the interval 0 to 2 pi into equal space, and the step is pi over 50. And now x is the x coordinate of the point on the circle, and y is the point on the circle, on the unit circle. And now I plotted. So this one will plot my unit circle. And this one, I just fill it with green, okay? Fill with green. So we know this is the domain. And then I said that, okay, that is the unit circle. And now I define the matrix A. So the matrix A is 1, 0, and 0, 4, right? Then now for every point on the circle, okay, so this is a point on the circle. So this one is a column vectors, yeah? So a point on a circle, on the unit circle. And I take the matrix A, I multiply with that point, okay? So I make a map into the image, and then I plot it. So I plot the image. So now I run it. So you see the circle got mapped into the oval, yeah? So that is what you predicted. And now what happened if I replace, you know, this one by something like 1, 2, 3, 4. Okay, so not a diagonal matrix anymore. And you see that it's still an oval, but it has been rotated. Okay. So now, so what is it going to do with the norm of the matrix? Well, remember we're talking about the unit circle, right? And you take the map AX, yeah? And now you just take the radius of the image. Okay, so the radius here is the biggest radius. Then it's the norm of the matrix. Okay, so that definition is a definition of the norm in the two norm. Okay, on the plane. So see, so now you can visualize what is the norm of the matrix. Yeah, at least in the two norm. So the norm of the matrix A is just the radius of the image of the circle, okay, of the unit circle under the map induced by the matrix A. Yeah. So got it? So now we go back to the slide again. So now the slide say that, okay, so this is my my matrix norm, right? So you see, you take the point W on the unit circle, you apply the linear transformation, and you got some oval shape, and you take the maximal radius, and that gives you the norm of the matrix. And it doesn't depend on the vector W, okay? So now why the second equal the third term? Well, because now, let me show you that is equivalent. So go back to the piece of paper. So now we have the definition of the matrix. Norm is max of a W, right? The norm, right? And W norm is 1, okay? And then my claim is this one is the same as AV, take the norm over V, okay? And V not equal 0. So V is a vector, okay? So now you can see that, okay, so if I write AV, yeah, it's just the same as A times V divided by the norm of V, and you multiply again by the norm of V, okay? When you divide, you multiply by the same thing, right? And then now I label this one to be W. Okay, so this one is W, right? And then I have V here as well, yeah? So now I have AV and, sorry, IW, yeah? And now AV, just IW times the norm of V, okay? And now what happens if I take the norm of the left and the right hand side? Now if I take the norm, okay, then I got something like this, yeah? And remember, now this one is just a scalar, okay? And if you remember the property of the norm of a vector, then the scalar can be pulled outside the norm. So you got this one will be V, yeah, pulling outside.
I'm done.
Question?
I'm good.
Everything is okay, right? And then this one is the norm of AW. Okay.
Get your head off it.
Okay, so everything is okay. Yeah, and this one is AV, norm. Okay.
Timing is so hard.
And then you just
Finding this so hard.
divide it.
Yeah.
You just divide it by v.
Yeah, sure. Come over. Come to the dark side.
You
And
divide
right
it
now
by
you're
v,
just
yeah.
doing norm. Norm.
And this one gives you the norm
This
of.
doesn't work. Yeah, it's just like. Yeah.
So this one gives you the norm of AW. Okay, but remember, norm of W is 1. Okay. And so now if you take the maximum, then they're just the same. So if you take the maximum, you know, I mean, if you take the maximum, then they're just the same.
Something.
So max of
Guacamole.
question, any question? So please type in the chat box, okay? So AV over V. Okay, so this is the non-zero vector V and equal max of AW for W has norm 1. Okay, so I just show you that the two definitions are the same. Norm of W is 1 means the length of W is 1. Yes, yes, but remember the two norm is the same as the usual length.
Basically.
But in general, you know, I mean, when I put the norm here, it can be any norm.
Just do this and you can read
Only one norm can be infinity norm. Yeah, can be P norm. Okay. So in the case of two norm, there is a distance. Right? But in general, it can be anything.
No.
Got it? Yeah. So the norm. So remember the norm of the matrix. You know, maybe you haven't seen it before, but it's just
we're gonna watch this one together.
Sorry, any question?
Yeah. I mean, I'm not taking it anymore.
Somebody said something.
Oh, I haven't dropped it, but mentally, I'm not having even you missed a nice little theory.
So somebody want to say something? David, your mic is on. Okay, so can David mute? Okay. Okay, so now I show you that you know, the two definitions are the same. Okay, and now go back to the slide here. So this is the what I want to show you, the norm of the matrix. Okay, so the norm of the matrix, remember this one is defined for any norm. Yeah, and in the case of the two norm on the plane when n equal 2, then this one is just the radius of the oval shape, you know, induced by mapping the unit circle into the plane under the matrix A. Okay. So this one is the example. So suppose I take the matrix is 1, 2, 2, 2. Yeah, then I plot the image. Yeah, then I got the oval shape here. So here's rotated to the right. Yeah. Then the radius of the red set is just the norm of the matrix A. Okay, but this one, the norm is the 2 norm. Okay. Okay, so now what is the consequence of the definition? So the norm of the matrix is just the smallest constant, so that when you take the norm of AV, that is smaller than the constant C times the norm of V. So why is that? Well, okay, so now I can show you that just the game of the definition. So now if I go back to my definition, well, before I go back to the definition, so let's see. So suppose you have AV, okay? Any norm less than or equal C times the norm of V, yeah? Then this one just means that, well, you can take AV divided by V, okay? Less than or equal C. So provided that V is not a zero vectors. Okay. And now you can take the max. So max of AV norm over V norm. So V non-zero still less than or equal to C, because this is correct for all the matrix, sorry, for all the vector V. So when you take the max over any V, it's still less than or equal to C. And now if you remember the definition, this one is just a definition of the norm of the matrix A. So A less than or equal to C. So in other words, the norm of A is the smallest constant, so that AV, when you take the norm less than or equal C times the norm of V. Okay, so the consequence is now you have AV and less than or equal the norm of A times norm of V. But remember, you know, when you write out like this, make sure you understand what is going on. So this is the norm of a vector. But this one is the norm of a matrix. Norm of matrix. Okay, so the norm of the matrix, the definition is a bit involved, but the norm of vectors can be defined by the formula we saw it before. Okay, so now, so any question? Any question? So this one just a consequence from the definition, yeah. So now go back to the slide, yeah. So now the matrix norm is just the smallest constant C, so that when you take the norm of AV and less than or equal to C times the norm of V. And now we can show that the norm of the matrix satisfies the property of the usual norm. So greater or equal 0, so that is obvious. And equal 0 if the matrix A equals 0, yeah. So you can show this. And this one, you can show this from the definition as well. So I think 4 is a bit tricky, but we don't spend time on this. Maybe we just skip this. Okay, so the norm of the matrix satisfies this triangle inequality. So here, remember, this is the sum of two matrices. This is the norm of the matrix. Okay, so now I want to show you in some special case, you can compute the norm by a formula. So remember before it's a definition, and now this is a theorem. Yeah, the theorem is the consequence of the definition. So now let me show you what does it mean here. So here, the formula just say that when you take the one norm, okay, when you want to compute the one norm of a matrix, then it just equal the max of the column sum, but in absolute values. So let me show you how it works. Yeah. So maybe suppose you have a matrix. So let me write on a piece of paper because it's easier to explain on a piece of paper. So now suppose I have a matrix A, okay, equal 1 here, minus 2 here, and 3 minus 4 here. Yeah. Then I take the so the one norm, okay. It just I take the absolute value of the first column. Okay, so will be 1 plus 3, and take the absolute value of the second column. So what is absolute value of 2, absolute value of 4, and you see that max, yeah, so max. So this one is just max of 4 and 6, so it just equals 6. Okay, so remember the number 1 here. So number 1, yeah, it just look like the column. So that is how you remember, yeah. Okay, but we can prove it. Okay, we can prove it. Why is the case? So maybe you can look for the proof in the general case in the lecture notes, but now I just prove for the case of 2 by 2 matrix. So remember 2 by 2 matrix is the simplest case you can have. You have A, B, C, and D. Okay, so my claim is that the norm, the one norm of the matrix A can be computed by max of A plus C in absolute value of B plus D. Okay, so you just take the absolute value of the first column and take absolute value the second columns, and you take the maximum, and it's just equal to one norm. So why is that? Okay, so now I approve it in a general case. So this one, I assume that every number is just a real numbers. Okay. So now suppose I take a vector v, yeah. So any vector v, then what is AV? So let V is say V1, V2. Okay, so then what is AV? So AV is just equal A, B, C, D times V1, V2, right? And if you remember linear algebra, so this one is just A, you multiply by V1, yeah, plus B multiplied by V2, right? And similarly, CV1 plus DV2, right? So this is just linear algebra, first year linear algebra. And now I take the norm of AV, the one norm. And if you remember the one norm, you just take the entries, yeah, of the vector in absolute value, and you sum it up. So it will be equal AV1 plus BV2 absolute value, okay, plus CV1 plus DV2 in absolute value, okay. And now, so what do I have here? Well, I can combine, well, I mean, maybe let me use triangle inequality first, yeah. So I say that, okay, this one will less than or equal absolute value of A, absolute value of V1, because, you know, I mean, the numbers can be positive or negative. So we have to be careful now, okay? So we take absolute value of BV2, absolute value of C, V1, absolute value of D, and absolute value of V2, okay? And now you can combine the terms. So you can have A plus C in absolute value times V1. Sorry. So you can see that, right? So this one is just V1, yeah? And plus B plus D V2, right? And now I can make another estimate. Yeah, I say that, okay, so now, you know, those two quantities, you know, A plus C and B plus D, if I take the max of two values, you know, I don't know which one, you know, but I just take the max value of two of them. Then it will be the upper bound, and you have only V1 an absolute value plus V2. Okay, you see it? So now what is the last one? The last one is just max of, you know, A plus D is the first column in the in the absolute value, and this one is just the second column, sum in absolute value. And the last one is just the v, the vector v, but in the one norm, right? So now I divide the left and the right by the norm of v, the one norm, yeah? So if I divide it, then I have a v1 divided by v1, yeah? Less than or equal max of a plus d, sorry, a plus c, yeah? b plus d in absolute value. Okay. And now I can take maximal over on the vector v, right? And if I take the maximal over on the vector v non-zero, then what I have is just the norm of a in the one norm. Okay, less than or equal max of a plus c in absolute value, b plus d, right? So this is the consequence, yeah? So you got it? So are we done yet? Are we done yet? Anyone? Are you still there? So are we done? So that means that yes, we are done. Did we prove it yet? Did we prove the statement? So my statement is, remember, so if you look at the statement, what I want is I want to prove the one norm of the matrix A equal this max of A plus C in absolute value of B plus D. So right now I just got less than or equal. So it's not done yet, okay? So what I need to do is I need to prove that equality can achieve. Yeah, then I will be done. So right now I just have the one norm is less than or equal this absolute values column sums. Yeah. And now what I need to do is to show that equality can happen. Okay, so now the second step is I will say that, okay, so now my matrix A again. So remember this one is just a 2 by 2 matrix. A, C, B, and D. Yeah. So now without loss of generality, I can assume that A plus C, okay, what is the first column sums in absolute value is greater or equal the second column sum. Okay, so then I have max of A plus C, B plus D in absolute value. Now it just equal the first column sum. Okay. And now I choose V star to be 1, 0. So the first unit vectors. Then what is AV star? So AV star now will be ACBD, yeah, ABCD, yeah, time 1, 0. So it gives me the first column, AC, yeah. Okay, and now what is AV star in the one norm? So what is AV star in the one norm? So remember the one norm of a vector is just absolute value of the first entry plus the second entries in absolute value. Okay. And now remember we say that, you know, I mean, this one is always less than or equal the norm of the matrix A, yeah, time the vector norm, the AV star, one norm, yeah. Okay, so remember the very theorem we just discussed before. So then, now what is V star in the one norm? What is a V star in the one norm? Well, remember V star just 1, 0. Okay, so just 1 plus 0, so just equal 1. Yeah. So then, what is the consequence? So the consequence is you have A plus C in absolute value less than or equal the norm of A in the one norm. Remember, you know, V norm is just equal 1. So that is what I have. Yeah. But remember, this one is what? This one is just max of A plus C B plus D, right? This one, this quantity, okay? Less than or equal the one norm of A. Okay, so before we show that, you know, the one norm of A is less than or equal this quantity. And now we show that this one less than or equal the one norm of A. So the conclusion is it has to be equal. Okay, so the conclusion is now we have to have the one norm of A has to be equal max of A plus C in absolute value B plus D. Okay, so that's what we want to prove. Yeah, is it clear now? So that is what we want to prove, at least for the 2 by 2 matrix. You show that the one norm can be computed by taking the max of column sums and absolute values. Okay. And if you look at the lecture notes, you know, there's a proof for the case n by n matrix, but the idea is the same. So once you understand it, what is going on, then you can get it. Yeah. Okay, so go back to the lectures. Yeah. So now, so I showed you that, you know, you can prove the first formula. So remember, this is not a definition. The definition is the quotient of the two norms or the max norm of AW and W is on the unit circle. Okay, but this one is just the consequence of the definition. And you can show that the infinity norm of the matrix, okay, is you do the maximal, but now the absolute of the row sums, okay? not the column sums. So remember number 1 here look like a column, so that's column, and then the infinity is just a row sum. Okay. So now we can compute what is the one norm, what is the infinity norm of this matrix. Okay. So now if you now I can take the, maybe you can do that as well, or maybe let me do it on the piece of paper. Yeah. So now suppose I have A equal 1 minus 3 4 2 0 1. So this one is a 3 by 3 matrix. Minus 6 8 1. Yeah. Then the one norm of A, okay? Just max of, and now you can sum up in absolute value. So this one is 1, 2 is 3, 3 plus 6 is 9 in absolute value. And this one 3, 8, 11, and this one is 6, so it will be 11, yeah? And infinity norm is, so now we have to take the row, okay? So max of, so the first row in absolute value is 1, 4, 8, so 8. The second one is 3, okay? So 3 come from here. And then the next one will be 9, so 9 and 15, that equal 15. Okay, so that is the infinity norm of the matrix. So for the one norm, take the column sum, and then in absolute value, and then take the maximal over the infinity norm. You take the rows, take the sums in absolute values, then take the maximal value. Okay. So now we go back to the slide. So this is the example. And now we define a condition number. So condition number is defined to be this product. Okay, so remember now the matrix has an inverse. Yeah, and if it's singular, then the condition number is infinity because the inverse doesn't exist. Yeah. And then the second observation is, because you want the inverse of the matrix, so it has to be a square matrix. Okay. So suppose we have this matrix. So what is A inverse? So let me compute this one by hand. So you see that you see that if you have a matrix A, B, C, D, yeah, then there's a formula for the inverse of this matrix. Okay, so if you remember, so the first you take AD minus BC, the determinant, yeah, and then you just swap the diagonal entries. So DA, okay, and then off diagonal you just negate it. Okay, so now let me check whether the formula is correct. Well, I mean, if you take A, B, C, D, right, you multiply with D minus B minus C, A. This one is just a check, yeah, quick check. Then you have A, AD, yeah, so AD, yeah. So AD, okay, minus BC, yeah, and then CD and minus BC, so equals 0, yeah. And then you do it again, so now A minus B, B minus A, 0 here. Then next one is minus BC plus AD, okay. And if you divide it by the determinant, you got 1, 0, 0, 1 here. Okay, so this formula is correct, yeah. So now I want to use this formula to compute my inverse of my matrix. So remember the matrix is A is 1K minus 1 minus 1. then A inverse is just, so remember we have to swap the diagonal. So -1 come here and 1 come here. Yeah. And we negate the off diagonal, so become 1. This one become minus k. And do not divide it. Do not forget to divide it by determinant. So the determinant is -1. Yeah. So -1 minus k. So yeah. So A inverse is just this matrix. So now what is the one norm? So the one norm of matrix A will be, what is the one norm matrix A? So it will be max of 1 plus k in absolute value, and the second one is just 2, right? And remember, if we remember the condition that k is bigger than 1, yeah? So if you look into the example, k is bigger than 1, so this one is just 1 plus k, right? Because 1 plus k now is bigger than 2. Okay, and what is A inverse in the one norm? Well, so now we have to remember 1 over k minus 1. So I don't take the absolute value because k bigger than 1. So this one is a positive number. So you can take the absolute value, but it's still the same, yeah? And now max of 1 plus k. Okay, now I don't take absolute value of k because k is bigger than 1, yeah? And max of 1 plus k and 2. So this one will be k plus 1 over k minus 1. And then the condition number in the one norm is just equal the product of those one norm of A and one norm of A inverse. Okay. And then now will be 1 plus k square over k minus 1. Okay, so this is a condition number. So you see, what is the formula here? So the formula is 1 plus k squared over k minus 1. And when k is very close to 1, then the condition number can be very big. Okay. And if you look at the matrix A, when k close to 1, then the matrix close to be singular, right? Right? I mean, if you have 1, 1 here, -1, -1, then the two columns, are just multiple of each other. So it's become a singular matrix. And if a singular matrix, then the condition number blows up to infinity. So it makes sense, yeah? So when k close to 1, then this one close to 2 over infinity. Okay. So any question so far, so good? Stay with me? Or fallen asleep already? Okay, so now the next slide will be, I mean, if the condition number is very big, then you say that the ill condition matrix. Okay, so we say ill condition when the condition is like order 10 to the 8, 10 to the 9, 10 to the 10. Yeah, so when condition number is like 100 or 1,000, it's still a well-conditioned matrix. Right? Because this definition is a bit vague, because you cannot say how much money you have is considered to be rich, right? I mean, you have $1, then, well, you're not rich. But you have $1 million. Does it mean that you are rich or not? You never know, right? So that, but if you have $1 billion, definitely you are rich. You're billionaires, yeah? So now even the condition number depends on the norm of the matrix, but they're equivalent. So in the sense that if you look at this inequalities, so if the condition number in the one norm is big, yeah, then the condition number in the two norm is big as well by this inequality. It's bigger than the condition number in the one norm. And if the condition number in the two norm is big, then by this inequality, condition number in the one norm is big as well. Okay, so we will prove this in the tutorial the next week. Okay, so you can check by doing this now if you want to. So now I have a few properties, okay, related to condition number. So let's see, we have time to do it or not. So maybe we can do a few of them, yeah. So the first one. So let me try to do it. See whether we have time. Hopefully we have time. So we do it on a piece of paper. So first we show that if you take a product of a two matrix and you take the norm of the product, then it less than or equal the product of the two norms separately, yeah. Okay, so how do we show that? Well, by definition, so you have a B norm is max of A B V divided by V norm 0, non-zero vectors. Okay, so this one is just a definition, yeah. So and this is true for any norm, yeah. And now we remember there's a theorem say that, you know, AX norm less than or equal to the norm of A times the norm of X, yeah, any X. So then I can apply to X equal BV. So then I have ABV will less than or equal norm of A times the norm of BV. Okay. So now I put it in right here. So I put it in right here. So less than or equal norm of A times norm of BV over V norm, yeah. Less than or equal max of V not equal 0. Okay, so this one is the reason, yeah. And now you look at this quantity. So A here doesn't depend on V, yeah. The norm of A, sorry, the norm of A doesn't depend on V. So I can pull it out. So I take this term, I pull it out here. Then what I have is just norm of A max V not equal 0, BV norm over V. Okay. And if you remember the definition, so this one is nothing but the norm of V, right? So we just play with the definition. Yeah. So we start with the norm of AB. We start with the norm of AB, right? And we apply the inequality and we end with norms of A times norm of B. Okay, so that is what we want to prove. So any question? So maybe we should stop here, yeah? So maybe there's a lot of theory already. So, okay. So I stop here and I let you ask question